video, we would be discussing about few concepts that would help us to understand devices made of semiconductors. When we analyze various electronic devices around us, we could find that the formation of such electronic devices requires putting together of dissimilar materials. Materials could be semiconductors, metals, or insulators. The importance of understanding this interface is that it affects the electrical property of the devices. The interface of dissimilar materials will form a junction. The best example of such a junction is the PN junction, which forms the diode. Even in the case of diode, in order to give biasing to the diode, we need to connect this PN junction to the external battery source. In order for that connection, we will have leads made of metals attached to the P-type and N-type. Even that interface of the metal lead to the semiconductor, that also forms a junction. The junction between a metal and a semiconductor can act in two fashions. It can behave like a diode by conducting only in one direction, or it can behave like an ohmic contact where it can conduct in both directions. If the junction between metal and semiconductor is behaving like a diode, it is known as a rectifying contact. Otherwise, if it can conduct in both directions, it is known as ohmic contact. In order to understand more about metal semiconductor contact, we will consider an ideal junction with no defects, which is the behavior of an ideal metal semiconductor contact depends on the relative values of work function of metal denoted by phi m and work function of semiconductor denoted by phi sc. What is work function? In case of solid state physics, it is the thermodynamic work done to take an electron from a solid to a place in vacuum just outside the solid. It is the distance between Fermi level and vacuum level, and it is denoted in the unit electron volt. The most important rule in the formation of a junction is that the Fermi level of the two materials should line up at equilibrium when a contact or a junction is formed. Let's take the example of forming a junction between two materials, molybdenum and platinum. As you can see, the work function of molybdenum is smaller when compared to platinum. So when we make a contact between these two materials, electrons from molybdenum will move to the free states in platinum, so that there will be positive charges in molybdenum when the contact is materialized. And because of these positive charges, there will be a contact potential generated at the junction. And this contact potential will be the difference of the work function of these two materials. So in this case, the contact potential will be 1.16 electron volt. Now let us see an example of a contact made between metal and semiconductor. As I had mentioned earlier, when a metal and a semiconductor is brought together to make a contact, there are two possibilities of behavior. It can act like a diode. In that case, the junction formed is known as the rectifying junction or Schottky junction. And the second behavior could be like an ohmic junction, where the current can move in both directions. In our example, we are taking a metal and an N-type semiconductor to form the junction. As you can see in the diagram, the Fermi level of the semiconductor is higher than that of the metal. This is because the work function of the semiconductor is lower when compared to the metal. As we had seen in the case of the metal-metal junction, here too at equilibrium, the Fermi level should be lining up. In order to Fermi level to line up, electrons from semiconductor has to move to the metal, the free space in the metal. And this will leave positive charge ions on the semiconductor side. And in the metal side, there will be negative charges. The metal junction, the electrons, due to the high density of electrons in case of metals, the electrons from the surface of the metal was moving to the other side. But in case of semiconductor, the density of electrons is lesser, and because of that, the movement of electron is not just from the surface but till a particular depth. The electrons move from a particular depth inside the semiconductor towards the metal. Thus, when a Schottky junction is formed between a metal and the N-type semiconductor material, the Fermi level lines up. And also, since the electrons from a particular depth of semiconductor is moving towards metal, the depletion region is extended towards the semiconductor. And because of this, there will be a bending in the energy band diagram on the side of the semiconductor. The bending in the energy band is happening in the direction of the electric field. As you all know, the electric field is from the positive side to the negative side. So the bending up happens as we move from N-type semiconductors towards the metal. The work function of the metal remains constant, but that is not the case of semiconductor. It depends on the doping concentration. So on joining a metal and a semiconductor for a junction, the Schottky barrier, which is given by phi b, can be mathematically represented as phi m minus phi n. Instead of phi sc, we are putting phi n because we are taking N-type semiconductor. So phi b is equal to phi m minus phi n plus Ec minus Efn, which is dependent on the doping concentration. This can be summarized and written as phi b is equal to phi m minus psi n. Psi n is the electron affinity. What do you mean by electron affinity? It is again the work done to take in an electron from the vacuum to the bottom of the conduction band of the semiconductor material. That is the electron affinity. Now let us explain how a metal and an N-type semiconductor, when joined, acts as a rectifying contact and an ohmic contact with the help of a band diagram. When we combine a metal and an N-type semiconductor, it will act as a rectifying contact when phi m, which is the work function of metal, is greater than phi sc, which is the work function of the semiconductor. And on the contrary, if phi m is less than phi sc, it will act as an ohmic contact. Now we know that whenever a metal and an N-type semiconductor is joined to form a junction, the Fermi level tries to line up at equilibrium, and there will be a bend at the energy band diagram on the semiconductor side. This we had seen earlier. Now, what happens if we are giving external voltage? On forward biasing, the Fermi level of the metal is lowered so that electrons can easily move from semiconductor to the metal, which means the barrier potential is reduced. On giving a reverse bias, the Fermi level of the metal side moves to an higher level so that the barrier potential increases, and that will make the flow of current difficult. That is why in the VI characteristics of a diode, during forward bias, there is a conduction of current, but in the reverse bias, there is only a small current flowing. That was regarding the metal semiconductor contact acting as a rectifying contact. And for that, if we are making a junction between metal and an N-type semiconductor, phi m should be greater than phi sc. Now, the flip side of it, if phi m is less than phi sc, it will act as an ohmic contact. In case of ohmic contact, where phi m is less than phi sc, the electrons will move from metal to the semiconductor freely because of its low energy. And so this will act as an ohmic contact, which means it obeys Ohm's law and current can move in both directions. And because of that, movement of or the VI characteristics will be a linear line. Whenever you increase the voltage, the current increases, which means it obeys the Ohm's law. Thus, we have seen various aspects related to the metal semiconductor contact. We have taken the example of metal and N-type semiconductor, which can be also mapped to metal and P-type semiconductor contact. So this discussion will enable us to understand more about devices where we use semiconductor and metal contacts.